Okay, this is where we left off last time. We're knocking on the door of integration, so we're building up its idea. We really want to understand the big picture of it before we get into all the details. So and then as you're getting into the details, you never want to lose the big picture, right? You never want to lose the big picture. And the big picture is that the value of a quantity or an amount of change, so what is that? The y, the accumulated quantity on our right graph, can be calculated as the sum total of many bits of change. That's the idea of accumulation. So we looked at tax due. So two ways to think about a total amount of tax due. You can think about it just as an output of a function, some tax function, right? That piecewise linear function. You plug in 58,000, boom, it tells you what your the tax due is. That's one way to think about an accumulated amount. But now we're seeing there's a different way to think about that, and as in January, bit by bit by bit, you made money, so your tax grew bit by bit by bit. And then in February, it continued. You made money bit by bit, so your tax grew bit by bit. And so then the total tax due on 58,000 is the sum of all those bits of tax that accumulated starting from January 1st to whatever date it is. Okay, same with the and so then we saw this this notation. The sigma means sum. Since they're all the same, they all look exactly the same, let's just write that thing once, delta tax. And then this sum thing will tell us that we're summing up a bunch of those. Okay? Height of the basketball after 6 seconds. So we have a function, some piecewise linear function. We plug in 6 seconds. It tells us the height of the ball. But now we have a new way of thinking about that. As little bits of time go by, we get little bits of height that accumulate. And so if you add up all those accumulated bits, you get the total height of the basketball after 6 seconds. So in this case, the way I'm showing it here is, 12 bits of time, which would be a half second each. So it's how much did the height change in the first half second? How much did the height change in the second half second? Add all those up, and you get, you don't get 6. You get whatever the height is at 6 seconds. Again, we can use the summation notation to make it easier, not harder. All right, so summation notation isn't about something scary. It's about an easier way to write this. Instead of having to write out all those things, we have just a way to write that equivalently. A couple questions, yeah?
So the number on top of the sigma isn't the final number, it's just the number of steps.
How many? Yes. So if I had done increments of $2, there would have been what? The 29,000? 29,000 of these things added together. And I would have 29,000 here. If I had done increments of 50 cents, then I would have had 116,000 of these things added together, and this would have been 116,000. So it's the number of terms that you're adding together. Yeah?
So the I or J value below the summation, it wouldn't be a question when you use the height of ball 6 seconds. Couldn't you use it on 0.5 and have 6 on top of the sigma, or is that
no? This is a counter.
Okay.
This is not a value of time. Here's my pointer. So yeah, so you're thinking that you're thinking of the input variable, the independent variable time. So that's not what this is. This is a counter. It's just counting what term you're on. First term, second term, third term, fourth term, which is different than this input quantity in this case, which is time.
Okay.
It's just a counter. All J or I is, it's just counting terms. First term, second term, third term, up to the 12th term, or up to the 58,000th term. Okay, so this is the idea of an accumulation, okay? That accumulated amounts can be thought of as having accumulated bit by bit to get that final amount. And this is, we're talking about the math of representing that, right? It's a sum of changes in that accumulated quantity. Okay, so here's that rate of change function for the rocket-powered basketball, right? With the booster rockets. Okay, so here's a second graph, a rate graph, and the name of the function is R of B, the rate at which a bacteria population changed in bacteria per hour. Sorry, that shouldn't be there. Okay, at any number of hours after the first observation. So these are both rate graphs. The first one is the speed of the basketball, and this is the rate of change of bacteria in bacteria per hour. So my first question is, besides being a different context, one is basketball, one is bacteria, and besides that they're different colors, what are some other differences between these two rate functions? Matt?
The one on the left, the one relating to the basketball.
Yeah.
And height and all that stuff, it's just breaks up into steps. Versus
Okay.
the other one, which is always continuing.
All right, so the steps then mean what about the rate of change? What do we have in terms of rate of change? Yeah?
It like pops. It doesn't necessarily like it goes from one value straight to the other. It's just like
Okay, so we have abrupt increases in rate, but then within each interval, what can we say about the rate? Adam? Constant rates. So that the basketball and the tax example were based on constant rates that, like she said, when you got to the end of the interval, boom, it jumped to a new rate. Okay? But the key is in each interval, we had a constant rate of change. And then Matt says, so what about the rate of change here? Is it constant? This is rate of change. It's continually changing. Every moment it's changing, right? Every moment that rate is changing. It's either going up or going down. It may pause for a second there, but the rate goes down. So it never stays constant for any interval of time. That's the big difference here. Okay? So if we want to track the population of bacteria, so we want to kind of do what we did over here, what we had the speed of the basketball, and we wanted to track its height. We want to build a function for the height of the basketball. Same thing here. If we have how fast the bacteria is changing, and we want to know how much of the bacteria we have, then what's the obstacle with this right here? What's the obstacle? Yeah?
There's not an exact. We have to find the exact rate of change for that given point. We can't have
Okay.
exact seconds.
And do we have, and so, and what do we have to find amounts of change? What is it we're using to find amounts of change? Delta y equals, and what is that based on? What is K? A constant rate of change. So we've been hammering this constant rate of change. Why? Because it can easily generate for us amounts of change in our quantity that we're focused on. But what's the problem? We don't have constant rate of change. So we can't use this. We can't use this because we don't, as soon as a little bit of time goes by, K is different and is continually changing. So we need that K to stay constant for a little while so that we can say, okay, what was that change in X times that constant K? That'll give us that amount of change for that interval. So our problem here is the mathematics that we have for accumulating the amount depends on constant rate of change, and this is a continually changing rate. Okay, so what are we going to do? So based on what we have so far, we're going to need constant rates. So what we're going to do is we're going to use our accumulation approach that we've learned so far with the tax and the basketball, and we're going to take this changing rate function and we're going to make it look like one of those. We're going to create a pretend rate function. It's pretending to be this one, but it's made up of constant rates. So it will be like the ones we're used to, and then we've got the mathematics of delta y equals k delta x, and we can use it on that pretend rate function. Okay, so what do I mean? So just real generally here, it's like, okay, maybe in this first little interval, we'll just guess the rate to be here, and we'll just say, okay, constant rate like that. And then constant rate down here like that. That's supposed to be constant. Oh, I didn't mean to do that. Here we go. Okay, let's try that again. So like, say in this first little interval, so here the rate is about like this. So, wow, it's really bad. Okay, and then maybe it's about like this. I'm trying to draw these straight. And then down like this. And then like this. So do you see that I'm using constant rates to simulate this given changing rate function? Do you see that? So maybe like this. What's that? So it will have breaks, yes, like the. So now this is just the idea, okay? So don't get technical here. I'm just giving you an idea of what we're doing. And what I'm doing is I'm making a new function that's trying to be like the pink one, but made up of constant rates. Does that idea make sense? I'm right. So this function has the same x quantity, has the same output, this rate of change, same rate of change output quantity, and it's trying to be like Mike, right? Want to be like Mike, all right? But boom, boom, constant rates instead of continually changing rates. And then on each of those intervals, I can use delta y equals k delta x because I have a constant rate on each interval. Does it make sense? Okay, now, actually doing that mathematically poses a challenge for students. So, but many of the things we've done up to this point are to get us ready for this. But let's practice one more time. So here's the situation. The name of the function is r of b. That's the name. This is the r of b function, or rate for bacteria. And I've got a segment here, and then a corresponding change. I've got a point here, q, and a point p. And in order to progress from here, to do the next thing we want to do, you need to be able to know how to write the coordinates of p and q and an equation for segment s. This is your little quiz test to see if you're ready for what we're about to do. Okay? So can you, and everything relates to the x values of 1.5, 2, and 2.5. Okay? Everything you do here when you write the coordinates of p, the coordinates of q, and an equation for segment s, they all relate to these x coordinates and this function r of b. So here's your test to see if you are ready for, it's your gateway. This is a gateway to the next thing we're going to do. You've got to be able to do this. Everyone give it a shot. What's the coordinates of p? Coordinates of q? The equation for s as they relate to these x values and r of b. This is review. Should be able to do it. Should be able to do this. Okay, what are the coordinates of point P? What are the coordinates of point Q?
1.5.
Okay, so the point is not to predict. It's not to guess from the scale, okay? I'm going to get rid of this. It's not to guess. It's exact coordinates. Exact coordinates. Is that what it is? Is that the y coordinate of P? R of 1.5?
Yes.
No, it's not.
Wait, what?
Isn't it no, it's actually S.
Where is R of 1.5? Where is R of 1.5? This y value. That's R of 1.5. This y value. Okay, keep going. This is the point on the curve at 1.5. So this y value is R sub b of 1.5. That's not the y value of p. That's why we're doing this.
I guess.
And so the y is r 2.5 for q, right?
Yes.
So that's where it is on the graph, like down.
Hey, Professor, I think they got it.
Okay, cool. Where's Alexis McKay? Alexis, look over there. How'd you do on point P? What's the x coordinate of point P, Alexis? 1.5. I hope we all got that. The x coordinate of P is 1.5. I agree. So now the trickier part, this is where we really have to be able to see this and be able to do this. What do you think the y coordinate was? No, it's not about estimating. So that's why I took the scale off. It's about using the function to get that y coordinate. Yeah. She wants r sub b of 2. So we're asking about the y coordinate of point P. Is it r sub b of 2? Yes. The y coordinate of the graph when x is 2 is the same as the y coordinate of P. If those are your choices. If 1.52 and 2.5 are your choices, that's it. R sub b of 2. How many got it before we talked about it? Okay, pretty good, but we need to be everybody. So now, let's do Q.
But with equation 1, couldn't you do the same thing to the other side of the equation? Like you have the one hill on the other side, so you'd be like.
But I told you it was about 1.5, 2, and 2.5 were your choices. Everything related to those x values.
Gotcha.
So yes, you're right. You could also come over here and say there's some x coordinate that gives you that same y here too. Yep, you're right. Okay, where is Ariana, Barisha? How'd Q do? Q go? What do you think for Q? X coordinate? 2. And what do you think for the y coordinate of point Q? She wants r sub b of 2.5. That's the y coordinate for point Q. It's the y coordinate of the function when x is 2.5. Do you see it? And if you didn't, is it starting to make sense? Can you start to recognize it from here on out? Really important. Questions? Okay, how did S go? So now I'm going to write the equation of this horizontal segment. Anybody get it? Let's see. Equation of a horizontal segment. Where is Renee Robles? Renee? You don't know? Okay. How about Ivan Portillo? Okay.
I don't know either.
Don't know. So how about just the general structure? So again, when you have something to do and you don't feel like you have to get it right, and the first thing you write down, think about the overall structure of it. If we want to write the equation of a segment or a horizontal segment or line, what will the structure of that be? Just in general. Y equals. So just do that much. Just do that much. I know. So you say, I don't know, but it's y equals something. It's y equals something, and that's a start. Okay, so y equals what? R sub b of 2. And if we really want to get the segment, then we do from 2 to 2.5. How many people got that before we did it? Okay, good. So we're making progress. So this is a crucial skill that you have to look at the function and pick off y values of the function that you're going to use somewhere else. You're going to use somewhere else, like at point P or point Q. All right. So right here, what are the coordinates of this point? Tell your neighbor right there. What are the coordinates of that point right there? X coordinate, 2.4. Y coordinate, R sub b of 2. Hopefully we all got that one, or 90% of us.
Yep, I did.
It has the same y coordinate as what? The function when x equals 2. So that's r sub b of 2. What's the y coordinate at this point?
Still R sub B of 2.
What about this point? What about this point?
R sub B of 2.
R sub b of 2, all those points on that segment. That's why the equation of the line is? Because that's what happens for every point on that segment. Its y coordinate is r sub b of 2. That's why the equation is y equals r sub b of 2. Because every y coordinate of those points is r sub b of 2. Okay, so now we're ready to make our first crack at creating one of these pretend rate functions. Any questions before we do that? Are we ready? Okay, so we're going to use intervals of 0.3 hours. So let's break those up first. And those will be our like delta x, right? Our change in number of hours. So 0.3, 0.6, 0.9, 1.2, and we'll just go up to 1.5. We'll stop at 1.5. So our delta x is 0.3 hours. And here's how we're going to get this constant rates. In each interval, the pretend rate is going to be the actual rate at the ending time, or the right side of the interval. So in this first interval, what is the x value of the ending time, or the right side? 0.3. The right side, or the ending time, is 0.3. And so we want to use the actual rate at 0.3 to be the pretend rate for the whole interval. So what will the pretend rate be for 0.1? How would you express the pretend rate at 0.1? So here we go. So what is the actual rate at 0.3? What's the actual rate? I want an exact value for the exact rate. R sub b of that. Those coordinates are 0.3, and the actual rate there is r sub b. Now I want to use that rate to be the constant rate for our whole first interval. So I'm going to use that rate to be a constant rate of change for that whole first interval. So, and that will be our first pretend rate. So at 0.1, the pretend rate will be exactly what? The pretend rate. R sub b of 0.3. And at 0.2, the pretend rate will be r sub b of 0.3. And at 0 seconds, 0 hours, r sub b. So there's our constant rate in the first 0.3 hours, the value of which is r sub b of 0.3, or the actual rate at the end of that time interval, to be the constant rate, or the pretend rate, for the whole interval. And we'll call that K1. So K1 equals r sub b of 0.3. So now, you want to continue like this. First determine what's the value of the rate, the value of the pretend rate in each of the remaining 4 intervals, and then make a sketch of that pretend rate as a constant rate for that whole interval. Go. So can you do it? So for each of the remaining 4 intervals, find the rate that you're going to use, express the rate you're going to use as the constant rate, and then sketch that constant rate in the interval, and you're going to repeat that 4 times. See if you can do it. Work together. See if you can do it. Just one more time. And then go ahead and use the scale to kind of get a number. Like for this first one, pretty dang close to negative 500. Okay. So then after you write down the exact rate for each interval, then use the y scale to just pick off a number that's close for that rate. Okay, let's see how we did. Where's Cody Short? Cody, how'd interval 2 go? What's the exact rate that we're going to use for the whole interval number 2? 0.6. So we go to the right side of the interval, x equals 0.6, and where is r sub b of 0.6? Tell me when to stop. Right there. It's the y coordinate or the rate at 0.6. So then in our pretend function, what's going to be the rate at 0.5? RB of 0.6. And then at 0.4? RB of 0.6. We want a constant rate because we want to use the easy math of constant rate of change to eventually generate our changes in bacteria. So we want to make constant rates to make it easier on ourselves. Okay, and so is that about negative 400? We'll use that. You can say negative 350, something like that. 375? Okay. So how about interval 3? Where's Nicholas Williams? There's Nick Williams. Oh, there you are. How about what is the constant rate we're going to use for this whole interval number 3? R sub b of 0.9. The rate at the right side of the interval. And so that's up here. So at 0.65, what's our pretend rate going to be at 0.65? R sub B of 0.9. You see? Negative 100? Something like that. We're just getting a number for now. Okay? All right, so then hopefully we got the pattern. R sub B of 1.2. Are we in positive territory now?
Oh.
So, in our pretend function, so the actual rate, what's the actual rate at 1 hour? What's the actual rate at 1 hour?
0.
One. Yeah.
What's the, everyone should see it. What's the actual rate of change at 1 hour?
Yes.
Still 0.
I only heard one person saying it.
R sub B 1.2.
What's the actual rate of change after 1 hour?
0.
Actual rate of change is 0 at 1 hour. That's where it's crossing the x-axis. I kept saying actual. What's our pretend rate of change at 1 hour? R sub B of 1.2. 1.2. The whole interval is going to have the rate at 1.2. The actual rate is 0. Here's the point, at 1. Our pretend rate in that interval is based on the rate of change at the right side of the interval. R sub B of 1.2. I asked the right question, I guess. Okay, what is that? 200? Positive? 150, okay.
A little less than 200. 150.
Last interval. Okay? What are we going to use for the constant rate of change for that whole interval? R sub B of 1.5. Okay? So what is our pretend rate at 1.3? What's our pretend rate at 1.3? R sub B of 1.5. What is the actual rate at 1.3? What is the actual rate of 1.3?
About 150.
Yep, it's going to be R sub B of 1.3, which is about 150. But our pretend rate is going to be down here.
And we do this just to have some sort of constant value.
Right, so that we can use, so now if we want to talk about what is the bacteria population, we can calculate changes in bacteria population using delta y equals k delta x. But we can't use that if we have a continually changing rate, because k is a constant rate of change, right? K is constant rate of change. All right, so this is, and what do we say that is? 100? Okay, questions on this table? So now these black steps that I've drawn, these black steps, it's a new function that's trying to be like the given one, but it has constant rates. So we can use now constant rate of change, delta y equals k delta x, to talk about what the actual bacteria population is. Anybody have a question? So let's do that. So let's look at time. Now I'm going to tell you that this bacteria population starts out with 2,000. So let's, so bacteria population. At time 0, it started at 2,000. So, based on our pretend function, based on our step function, can you figure out what the new bacteria population is at 0.3 hours? See if you can do it. So, can you apply what we've learned? So, if it starts at 2,000, then based on this rate of change function right there, what will the new population be at 0.3 hours? See if you can do it.
Sorry, 1,600 more. Next one, 1,000.
Where's Sana? Kokar. Sana. Any idea?
Bacteria population at 0.3 to 2,000 times
2,000. So you want to take times 0.3. So 0.3. So let's apply the symbols here. What does 0.3 represent in this situation? 0.3 is not K. 0.3 is delta X. That's our change in time. So is the bacteria population changing at 2,000 bacteria per hour? That's why you would multiply by 0.3. So how is it? It's not changing at 2,000 per hour. How is it changing?
It started at 2,000.
Okay.
Bacteria increases, so it increased at a rate of 5.
What is the rate of change in the first interval? Negative 500. Which means the bacteria is doing what? Decreasing. So how do we calculate the amount of decrease in that first interval? K delta X. K delta X. You're going to take the bacteria per hour times how many hours? Bacteria per hour, K, times how many hours? 0.3 hours. K delta X. That gives us delta Y. All right, so we can go like this. We can say, okay, in that time interval, delta Y was equal to,
0.3.
no, K delta X, negative 500 times 0.3. So you had the right idea, but you had the 2,000 is not the rate. Negative 500 is the rate. So you had the right idea. Okay, how much is that amount of change? Negative 150. So in that time interval, the change was negative 150. Therefore, what's the new population at 0.3? 1,850. The change is negative 150. Delta Y is K delta X. So we got negative 150 for that change. Okay, next interval. How much did the bacteria change according to our pretend function? What's K? Negative 400. Delta Y equals negative 400 times. What's K? Or sorry, what's delta X?
0.3.
Still 0.3. It's another change of 0.3 hours equals.
Plus 1850.
Right. So that's going to be negative 120 this time. 1730.
Yes.
It should make sense, right? It should make sense. We've got a bacteria population. We calculate the change, and so then we add that change to get the new population every 0.3 hours. So this was 0.6. From 0.6 to 0.9, delta Y equals? Where are we at? Negative 100 times 0.3. 30? Negative 30. So are we at 1,700 now? At 0.9, we're at 1,700. Delta Y. Now we're finally going to go up a little bit, right? Here the rate is positive at, what's 150 times 0.3? 45. So therefore, 1.2 hours, 1745. Are you tracking? I'm not writing down every number now. Delta Y equals K delta X. The new population equals the old population plus delta Y. That's the two mathematical ideas here. delta y equals k delta x, and the new population equals the old population plus the change, plus delta y. What is this now? 100, delta, another 30 added?
Yep. So 1775.
1775.
It looks like 177.5 right there.
Yeah, it does.
That's better.
So what are we doing? We're creating this is the idea of creating not just an amount of bacteria, but an amount of bacteria function. We're figuring out in a table form, we're coming up with the amount of bacteria. It's really a distraction, you guys. Okay, so we're coming up, this is a table form of amounts of bacteria at any given time. In this case, every 0.3 hours. So this is the idea. We started with a rate function, and now we're creating an accumulation function. It's just in table form, right? That we have input of time, output of number of bacteria. Okay, any questions on this process? There's lots going on here. Yeah.
So we have to multiply the rate value by change in x.
Delta y, right. So you're going to take bacteria per hour times the number of hours gives you number of bacteria.
Very well.
Yeah, that's it. So it's delta y equals k delta x. Other questions? Can I erase this?
Okay.
Okay, so earlier we said that calculus is really about two goals. You know how much of something you have, and you want to know how fast it's changing. Or you know how fast something is changing, and you want to know how much of it you have. So which of these statements is what we've been working on since we started with the taxes and rocket basketball and the bacteria examples? Everyone think to yourself? Hopefully everyone gets this right. Do you know what we're doing? Is it you know how much of something you have, you want to know how fast it's changing, or do you know how fast something is changing, you want to know how much of it you have? Everyone think to yourself? A or B?
It's D.
It's what? How many people think it's A? How many people think it's B? Victory. This is what we're doing now. This is our endeavor. This is the idea of integration. This is the idea of integration. You know how fast something is changing. You want to know how much of it there is. Okay, so suppose you know the relationship of meters cubed per day of oil released into the ocean with respect to time and days since an oil rig started leaking. And here's that relationship. Okay, so it's time and days is our x-coordinate, our independent quantity, and the rate of change of oil being released, meters cubed per day, is our y-coordinate. And what is our goal in terms of this specific situation? What do we want to determine?
How much huge amount?
What's that?
How much oil is actually leaking?
How much oil is actually leaking? That's it. The total amount of oil in meters cubed leaked. Okay, that's generally the right idea, but we want to do better than that. So this is generally the right idea. But what do we want that's better than that? Anybody? So that's the idea of, okay, after 3 days, so just saying the total amount of oil leaked is kind of like saying, okay, after 3 days, what amount of oil is that? And that's good to know, but we want to do better than that. What's better than that? Okay, so
At any day.
a function at any day, right, at any day. A function that outputs that at any number of days. That's what we want. We want to have a function that says, oh, I want to know how much oil has leaked at 0.6 days. I want to know how much oil has leaked at 1.9 days or 2.6 days. Not just the total amount at the end, but a function that as time increases, we can track the oil being outputted into the water. Okay, so this is the rate of change function. It's one of our right-hand functions. And what do we want to build out of that? How much? But a how much function? A how much function? Accumulation function. Total meter cubes of oil at X days. That's what we want. And what's the difficulty? What's the difficulty of getting that accumulation function with this type of rate of change function?
It's not constantly changing.
It's not constant rate of change. The rate continually changes every moment. What's our solution? So the rate is continually changing. We need constant rate of change to find changes in quantity of oil. And so, right, what approach do we take in light of this difficulty? Steps. We're gonna make a pretend rate function with steps. Create a function of constant rate that pretends to be the given rate of change function. Okay, so we will work on that example Tuesday, but in the meantime, you'll have lots of homework over the weekend.